After all this Copernicus content, we shouldn't forget about the other stuff from Houdini 20.5. And we especially shouldn't forget about the new MPM solver. And although judging by the weather in Germany right now, a wet mud simulation would be quite fitting, I want to create something a bit more cheerful. I want to create a snowball. Before I actually jump into Houdini and create a snowball, I first of all want to quickly talk about in what cases we actually do want to use this new MPM solver, because it in some ways is quite similar to Flip and in other ways quite similar to Vellum, and so we need to find out where we want to use it compared to, well, Flip and Vellum. So this is my very unscientific graph. Down here on the x-axis we have the consistency of the thing that we're going to simulate from very loose to very solid. And in here on the y-axis we have the competence of the solver in simulating that. And so for example, if we take a look at a flip solver is very, very competent in fluids and viscous fluids. However, it's not really good for simulating grains or soft bodies, for example. And technically it is able to work together with the RBD solver in Houdini, so it gets a little bump in here for solids as well. Taking a look at Vellum, since this is a multi-solver, is basically a spiky boy. The two things that Vellum is used for best is soft bodies and grains. We have those two huge spikes in here. However, it is also somewhat competent in fluid and viscous fluids, just not as well as Flip, and it's also somewhat competent in solids, just not as well as RBDs. And you're mainly going to use Vellum if you're mainly going to simulate soft bodies on grains, and you want to have fluid or solids interact with those soft bodies or with those grains. This is where we're going to use Vellum. Now, where does MPM fall on this diagram? Well, it looks something like this. It's basically competent throughout the whole range of those material properties. It's just not very competent in any of them. So the only thing or the only case where we do actually care about the MPM solver is where we do want this large range of material properties. And it also has a nice party trick that materials that we're going to simulate can sort of move up and down this line down here and at one point act as soft bodies and at one other point act as grains. And this is exactly the thing that we're going to need for a snowball, because a snowball should start out here as a sort of hardish soft body while we're throwing it. However, as soon as we hit something, we want to have some parts of a snowball turn into snow chunks, into sort of solid objects that fly away. But we also want to have a lot of tiny debris, a lot of things that really acts like grains, and this will be our snowflakes. And the MPM solver in Houdini is the only solver that dynamically can change the properties of the thing that we're going to simulate without some very complex setups or without some attribute trickery. So let's actually build our setup. I'm not going to build this from scratch. I have a little scene prepared in here, and in the scene I have the colliding object, which will be this 3D scan of a statue of some dogs, and also the snowball in here, and also a camera. Let me quickly walk you through this scene right here. For my colliding object, I loaded in a 3D scan by 3dscans.com. You can download it right here. I brought it into the right scale using this match size node down here. I did some little tweaks, make it sit flat on the ground plane. And then I used this transform node down here, where I have the pivot set directly where I want to later hit my dog with my snowball. And I'm going to use this transform node down here sort of to change the impact angle of the snowball and get the shape of the spray of a snowball in the end that I want. And this was really helpful for dialing in the look that I wanted in the end. Then also, since this is a very detailed model and this is just useless data, or most of it is useless data for a simulation, I clipped away a lot of it. And for a snowball, I simply started out with one sphere. I added a mountain node to make this a bit more irregular, and then I just moved it to the right position so that I have to simply accelerate this down into the Z direction to hit the snowball where I wanted to hit. And this is my setup done. So now to set up our MPM solve, what we're going to do is we're going to get rid of this merge node down here, and instead I'm going to search for MPM configure. And we have a bunch of presets in here. However, the simple MPM configure up here will create for us the sort of minimal viable setup that we're going to need for our MPM solver. Let's drop this down, let's wait for it to cook, and in the end we get this. Let's first of all get rid of our dummy objects up here, we don't need those, and what we're left with is our MPM source, our MPM collider, MPM container. The source and the collider are pretty much self-explanatory. This is where our snowball will go, this is where our collider will go. And the MPM container is the sort of simulation space that we're going to set up. The MPM solver, in the end, is pretty much based around the flip solver in Houdini. So there's going to be some volumes involved as well, and volumes need a container to work right. Let's wire connections up, like this and like this. And now let's take a look at those options. And whenever I'm dealing with a new solver inside Houdini that I have not worked with yet, I'm basically going to look for three things, three sets of parameters. I first of all want to find all the parameters that I just have to set to a fixed value and just leave them as is. I won't have to change them to change the look. These are just set in stone based on the thing that I want to simulate. And let's quickly take a look at those first. And the first one will be our snowball size. And again, this is set up here on our sphere. And I set this to, in Houdini units, a value of 8 centimeters. And I think this is a pretty realistic size for a snowball. Then also on our MPM source, I can set up a material preset. And by default, this is already set up to snow. And I found this preset to be pretty accurate and to give me pretty good results without tweaking most of those values down here. Basically, any preset you set up here will set all those material parameters down here. Next, I can set an initial state, and I want to set the initial velocity. And again, I sort of try to find a real world value for this. Now, Googling the throwing speed of humans, you mostly get the result for athletes, which I think is not really realistic. So what I ended up using in the end is the max throwing speed of a chimpanzee, which is quite a bit lower than the throwing speed of human athletes. So I think this is pretty much what your average human can throw as well. And this boils down in the end to around 9 meters per second. So in the end, in here on our MPM source, on the z-axis, I'm going to add in a value of 9. And finally, there are some parameters on the MPM solver as well that I can just set, and this will be the time scale. So this will make a simulation either fast forward or slow motion. In this case, I want to have a slow motion animation, and I want to set it to pretty much 0.1. And the other thing that I want to set is the cache size, and I'm going to find this under advanced, and this is based on my computer's working memory. In this case, I have 64 gigabytes, and I'm going to set this to a conservative 55 gigabytes, like this. So these are our fixed parameters done. The next set of parameters that I want to take a look at are the quality parameters. The parameters where I can basically set how well my simulation works. Higher values in here should result in a better simulation, however, also a slower simulation time. And the main parameter that I'm going to work with here is the particle separation. And we're going to find this in a boundary. Now for my particle separation, I usually want to stick to two values. I want to have one low resolution value, and my main goal in here is that my simulation resolves fairly fast, and also the entire simulation over the entire timeline should fit inside my computer's memory. And for this setup right here, after a bit of experimenting, I settled down for a particle separation of about 0.0006, like this. Once I set this, both of my colliding object and my actual snowball get a lot more detailed. And on the snowball, if you take a look at the info panel, we have around 1 million points. Now for my final resolution, I halved this value, so 0.0003, and this resulted in around 10 million points. Again, since this is a sort of flip style simulation, halving this value right here will increase the overall data for a simulation by a factor of 8, and 10 million points resulted in around 20 gigabytes of cache data later, while writing this out to disk, and it's simulated on my PC for around 4 hours, which again I think is a sort of nice value for a simulation like this. Now, the next thing that we want to set in here is the domain size. And the domain size is again the maximum size of the volumes that are going to get used for the simulation. Now, by default, the MPM solver uses sparse volumes, so they will be a lot smaller. However, I think it's still a good idea to set some limits for those volumes. So what I ended up choosing in here are again some very specific values that I'm just going to enter in here. Something like this. And also to visualize the boundary, we can jump into a handles tool and take a look at a bounding box like this. And this is how it looks in the end. And the other thing that we need to do is we need to specify the right boundary type for boundaries. Because right now this is set to opened, and if it's set to opened, this basically does not have any effect at all. what I want to do in here is first of all check this check mark in here and set this to delete. So any particles that will move beyond this boundary will simply get deleted, will make our simulation a lot smaller, and also this is now the max size for our volumes as well. Now the other thing that you might change as quality parameters is the CFL and material condition, and you can find both of them down here on the MPM solver in this main solver tab. And what both of those do is basically adjust the substeps that our solver is going to take. Now the MPM solver in terms of substeps is pretty special because we usually don't want to set our global substeps in here. The solver chooses its own number of substeps dynamically frame by frame, basically on how many it thinks this current simulation step needs in the end. And this is set between 1 and 10,000 in here. And those values up here, the CFL condition and the material condition, basically control how quickly the number of substeps will ramp up depending on your simulation. A smaller value in here will result in more substeps, and a smaller value in here will also result in more substeps. You mainly want to adjust the CFL condition up here. However, if you're dealing with very stiff materials, with very solid materials, you might want to adjust the material condition down here as well. For this simulation that we're doing right here, right now, I found both of them worked very nicely at their default values. So I left them both as is. Now, finally, we're down at the last step of parameters that we need for a simulation. And these are the parameters that actually control the style of a simulation. And again, for a Snowball, the thing that worked nicely for me is first of all, on a Snowball itself, the critical stretch and the critical compression. And again, you can find those on the MPM source node in here. These are these two right here. And what those two parameters basically control is how quickly a Snowball moves from something that acts like a soft body or like a fluid that acts to a solid. Either because it's compressed or because it's torn apart. This is what this chunky preset does in the end. And what I found worked quite nicely for the Snowball is leaving the critical compression as is. However, I did end up lowering the critical stretch a tiny bit. And this in the end resulted in the Snowball breaking apart faster and resulting in a lot more spray and a lot more tiny pieces, which is what I wanted. And again, small steps in here is what we're looking for, so I'm going to set this to a value of 0.006 instead of 0.0075, like this. And the other parameter that controls the style that I like quite a lot is on the collider, the friction and the stickiness. These are two separate values in here. The stickiness basically controls how much of a snow will stick to the surface of our dogs and not simply fly away. And the friction will control how likely these sticking pieces are to slide down the surface of our objects. And again, through a bunch of experimentation, I found out that I liked for the friction a value of 0.3 a lot, and for the stickiness a value of 0.5, like this. And now we're pretty much all set with our parameters. The one thing left to do for us in here is to basically hit the display flag down at our MPM solver and to simulate this. And again, this will take a bit, but we'll see what we get. And let's also quickly set our background to dark so we can see what we're doing. And after a bit of waiting, we're left with a result like this. And I think this very much looks like a Snowball. I'm quite happy with this result right here. So the final thing left to do, at least for a simulation, is to basically go to our MPM container, reduce this particle separation by half, and then dropping down a file cache node, wearing this below our MPM solver, and writing all of this out to disk. However, again, this will take quite a lot of time. So what I'm going to do is I'm basically going to load in a finished sequence that I cached out earlier. Something like this. And as you can see, we have quite a bit more points to work with here. So let's take a look at what we cached out in here. First of all, this looks all fine. I'm also probably going to quickly show you a flipbook right now at this point, because this in the viewport plays really slowly. However, scrubbing through this flipbook or taking a look at it, we have one issue that we might want to solve. And we can see this at the first couple of frames in here. And what we are seeing here is a flat spot appearing here on a Snowball. So why is this? Well, the reason for this flat spot is basically a Snowball right here is hitting the boundary of its own sparse volume. And we can also sort of see this if we jump back to our simulation up here. Again, this is now a bit coarser. And we can go to the Visualize tab and we can select Show Background Grid. And this is the sparse volume that is created for our Snowball. And as we can see right here, we're right at the edge. And this is what in the end causes this flat spot to appear. So how could we fix this in simulation? Well, maybe there's a more efficient way. I'm not that experienced with the MPM solver yet. However, what I found sort of worked is to go to the advanced tab and first of all up the min-max voxel dilation value, maybe to a value of 15 on the minimum. This will increase the padding around our snowball. And also to go to the solver and to actually adjust the global substeps, because this padding will be calculated with every global substep, not with every substep the solver chooses in here. However, both of these values needed to be quite large and quite slow to give me decent results, and it's only a problem while the snowball is flying towards our dog, so I think since we're in Houdini right here, we can find an easier solution for this problem in the end. And to solve this problem, well, we're going to do a few steps. We first of all need one name attribute on our main geostream. And while the solver does have a name attribute that we could use in here, the source name, for my cache in here, since the source name, since we only have one source, is just one value, I removed it to make my cache files a bit smaller. So I quickly have to create one temp name attribute down here to make this work. So let's drop down one name node. And on this name node, set the namings or the name to temp, and let's set the class to point. And now we have one temporary name attribute on our geostream right here. What this now allows me to do is to first of all use a time shift node to grab the very first frame on a timeline. And to do this, I simply want to get rid of the channel in here, and I want to set the frame to 1. So this gives me this frame right here. And I can use this together with a main animated geometry and an extract transform node, if I wire both of them in here, to basically get a point that is exactly in the middle of a snowball that we're currently simulating. And I can use the output of this node and our time shift in here together with a transform pieces node to basically move this still geometry right here to the same position as our main snowball traveling up here. And with this, we can get rid of this flat spot. Now, I also want to copy over all those attributes that I still need. So to do this, I want to need an attribute copy. I want to branch out from up here, from this name node down to my attribute copy. And in here, since our number of points will probably change, basically as soon as those points are starting to exit a boundary, I do want to match by an ID attribute, which fortunately our solver creates for us, this ID attribute in here. So I want to enable this in here, and I basically want to copy over all my attributes. However, the one attribute that I want to leave out is the P attribute, because again, we want to get rid of this flat spot. So I'm going to uncheck allow P attribute in here. And now this is fixed. Now with this done, I can also get rid of my temp name attribute. Let's drop an attribute delete node for this. Get rid of our name in here. And finally, I can switch between my main file cache and my fixed flat spot, basically up until our snowball starts hitting something. So for this, I'm going to drop down a switch node. And I think our frame of impact is frame 11. So let's quickly move to frame 11 down in our timeline. Yep, now it's hitting our statue of our dog. So in here in our switch, I simply want to write $f is smaller than 11 like this. And now up until frame 11, we're using our fixed geostream on the right. And after that, we're using our main cache. So with this all fixed, I can now finally work on meshing my snowball for rendering later. And also for rendering, I want to have a mix between some solid chunks that will be just your standard Houdini mesh, and also a lot of particles, which will be my snowflakes. And I first of all want to work on my mesh. I'm going to create my mesh from VDB, and I'm going to create this VDB from particles like this. Let's wire this in here. And under the voxel size, I want to write a very specific expression that I simply grabbed from the MPM masterclass that SideFX published a couple of weeks ago. And this masterclass, or this special formula that I'm going to use in here, is basically the value that is here stored under a detail of our cache, this dx attribute, which in this case is a value of 0.006, so double our particle separation. And I want to divide this by 2 to make it an actual particle separation. And then I also want to divide it by a very specific value of 1.51. And this 1.51 is simply based on the minimum radius plus a little bit. And once I do this, I now have a nice particle representation of my MPM snowball. Now next I want to do a bit of processing. I first of all want to smooth it. So let's use a VDB smooth STF. And in here I basically use default values. These work nicely for me. And this does remove a lot of stuff from a snowball. However, I'm fine with this. These are the parts that I want to have as particles in the end as well. And finally, I want to make my pieces even smaller. So for this, I'm going to add a VDB reshape. And I'm going to set this to erode, and I'm going to erode by 1/2 of a voxel radius like this. And finally, to turn this into a mesh, I want to use a convert VDB node. And I'm not going to convert this into polygons, I'm going to convert this into a polygon soup because this is much more memory efficient in the end. Now this is my mesh for now. I do want to add some other attributes on it as well. Mainly a velocity attribute for motion blur and also a UV attribute for shading. However, to calculate these, I have to work on my particles next. So let's do this first. Now on my particles, I do have a velocity attribute. However, I have to make some changes to this velocity attribute because this is the velocity attribute as if our simulation would run in real time, basically with 24 frames per second. However, we made it a slow motion animation in the end, so we have to make our velocity attribute smaller as well. And the quickest and easiest way to do this is with a wrangle. Let's write this below our switch. And in here, let's simply take our v at v, our velocity, and multiply it by a value of 0.1, like this. And this is the same as our timescale. This is our velocity attribute done. The next thing that I want to add is some UVs. And for those UVs, I'm first of all going to use a time shift node to create or to grab one still frame. Again, the first frame, because on the first frame, our snowball is just a sphere, and the sphere is pretty easy to UV unwrap. So again, let's delete the relative reference or delete the channel. And let's set this to frame 1 like this. And we have this ball right here. And on this ball, I want to add some UV coordinates. So let's use a texture coordinate node, or UV coordinate node for this. I want to set the texture type to polar. The y-axis is fine, but I want to add my UVs to points like this. And to quickly visualize this, I'm going to use an attribute from map node. And yeah, we do actually see some UVs on a snowball now. Now, one problem that I'm seeing right here is that a UV seam is right down the front of a snowball, right where the camera is looking. So we can't have that. So to quickly fix this, I simply want to add one transform node in between those and just rotate my snowball a value of 180 degrees along the y-axis. So now let's add a different position. However, a UV is looking a lot better now. And again, I want to bring this over to my main animation, again using an attribute copy node. Let's wire this in here. Let's again match by ID, and let's bring over a UV coordinates like this. And finally, let's move those attributes also onto our mesh. And for this, I'm going to use an attribute transfer node. So wire this in here like this. Let's zoom in a bit, and the attributes that I want to bring in will be velocity V, and our UV coordinates UV. And to make those look a bit nicer, a bit less jagged, I'm going to go into the conditions tab and I'm going to set the max samples count up to 10. And now this is my mesh done. So I'm going to drop down another null and I'm going to call it mesh render. And I'm also quickly going to make this node tree a bit more clean. Something like this. Now, next I want to start working on my particles some more. And first of all, I want to get rid of all the particles that are stuck inside our main pieces in here. So for this to work, I'm going to set down a group node. I'm going to wire this below my attribute copy. Let's call this group solid. Let's set this to points. Let's disable our base group and let's enable keep in bounding regions. And as my bounding region, I'm going to set a bounding volume, and I'm not going to use a bounding object because this is way more complicated to calculate and way more slow to calculate. So I'm going to use a volume, and the volume that I'm going to feed in will come from a VDB reshape up here. So wire it up like this. And now all our points inside our pieces are now inside this group as well. And now we can get rid of them. Let's drop down a blast node and let's blast away these solid points like this. Now, what I want to do next, or what I want to do later down the line, is I want to again up this number of points a bit, basically add even more resolution to my snow and my snowflakes. And what I'm going to use here in the end is the point replicate node. And this node basically takes in each point and adds more points to it. It's basically a fancy copy to points node with some specific options in here. Now to set this all up, I first of all going to need some additional attributes on all of my points up here. First of all, I want to randomize the orientation of each snowflake in the end. And for this, I'm going to randomize the normal on each point. So let's drop down an attribute randomize node. Let's set the attribute name to n for normal. I want to set the distribution to directional orientation. And also again, since our point numbers are changing and we don't want to have any flicker, I'm going to add a seed attribute, and again I'm going to use my ID attribute for this. Now I want to do the same thing for my p-scale. So again, another attribute randomize. Let's grab a p-scale attribute like this. This is way too large. Instead I want to multiply it, and I basically want to multiply it between a value of 0.7 and 1.3 like this. And this can be a one-dimensional value, and again, under the options, I'm going to enable an ID attribute like this. So finally, with all of this done, I can move on to my point replicate node. However, before I wire this in, I should take a look at the parameters. I don't want to have 100 points per point, this is way too many. I want to just have a 5, and I also want to tweak the shape. And I want to make this a sort of squashed disk, so I'm going to go to the size and basically turn down the Y size to a value of 0.1. And I want to set the uniform scale to a value of 2. And also under the attributes, I just want to enable to copy all my source attributes onto my new points as well. So with all of this done, I can wire in my point replicate node, and as we can see right here, now we have quite a lot more points and quite a lot more resolution in our snowflake. The one final thing that I want to do in here is I also want to make the p-scale of my points again a bit smaller, because now we have more points per point. And again, I'm going to use a quick wrangle for this. Let's drop down a point wrangle. And I want to set f at p-scale times equal to a value of 0.5 like this. And these in the end are now my particles that I can move into Karma for rendering. Let's create our last null, and let's call it particles underscore render like this. Now this tutorial is already running long enough, so I'm not going to build this entire setup from scratch. Instead, I'm just going to quickly walk you through my Karma settings and what I did to get the look in the end. So first of all, to grab my render camera, I'm using a scene import camera. I'm not creating a new one inside Karma. Then I'm using here standard sub import nodes to import my collision object, my particles, and my mesh. And I'm also using one sub create node in here to create my backdrop. Then I have my materials, we will talk about them in a second. And then I'm just lighting this with a dome light. I'm using a camera edit node to edit the focus distance and the f-stop of the camera that I imported. And finally, this goes all into a Karma render settings node. And the only thing that we need to enable here on those render settings is under rendering, under camera effects, under motion blur. We have to enable velocity blur, both for our main snow objects and also instances of particles like this. So how can we make those particles look like snow? Well, let's jump into a material library and let's take a look. Let's first of all take a look at our snow material. This basically mostly is a Material X standard surface. And on that standard surface, I have a base color set to a very light blue. Then I have set the roughness way down to a value of 0. And then to actually make this look like snow, the main thing that we want to play with is the subsurface scattering. So in here I just played with the subsurface ratio up here and the subsurface scale down here until I found something that did look like snow in the end. And then I also gave my subsurface color this light blue color, the same as my base. And finally, to add some glints to my snow, all I did is basically create a very noisy normal image using cops that you can also find in the scene find download. And I added this as a normal map with a very strong scale like this. And this is basically my entire normal map setup and my entire snow setup done. And for my snow particles, this is even simpler. This is just all done in the Material X standard surface. Again, we have this sort of light bluish color in here in the base color. Again, we have 0 roughness on the spec color. And to sort of fake some subsurface scattering on our particles, since we can't enable it there, the one thing that I did in the end is turn down the opacity to a really, really low value, a value of 0.06. And this in the end gave my particles also a very snow-like, a very soft color. And this is basically everything there is to rendering and simulating snow inside Houdini. This has gotten a whole lot easier with the new MPM solver. You just have to sacrifice a bit of disk space and a bit of time to get there. But in the end, This, with very little tweaking, will give you very nice results, and I think this is a very worthy new addition to the set of solvers that we have in Houdini. But this is it for today, and until next time, it's cheers and goodbye. And if you like us and want to support us, or just want to learn more about Houdini in in-depth courses, consider becoming a patron of ours. And to everyone already supporting us, thanks so much, guys. Without you, and Hackma in this form would not be possible. Thank you.